Hello class, this is CSE-5720, section 2, week 6, fall 2025. Alright, your next lab won't be ready until next week, so in the meantime, I am gonna give you a filler assignment, homework 2. So, this is more practice with queries, and this is for chapter 3. These problems are adapted from problems in chapter 3, and they build off of one another. So here are your queries. Using the university schema, and I pasted it at the end of this document. So these are the schemas that you're going to be using, and these basically represent tables in your database. So for each of using these schemas down here, write a query for the following. So for problem 1, part A, find the names of all students who have taken at least one computer science course. The result should have no duplicate names. Problem 1, part B, find the names of all students who have never taken any computer science courses. Again, the result should have no duplicates. As a hint, use the previous query's result to help you build this query. Problem 1, part C. For each department, find the maximum salary of instructors in that department. Assume each department has at least one instructor. And number 1, part D. Across all departments' maximum salaries, find the lowest of those maximums. And as another hint, use the result of the previous query. So, this is practice for nested queries, basically. And that's problem 1. Problem 2 has more to do with updates. Adding new information to a database. So problem 2, part A, create a new course called CS-001 called Weekly Seminar, and it's worth 1 credit. Number 2, part B, create a new section for CS-001 with a section ID of 1. This section is for fall 2009. Number 2, part C, find the computer science student with the highest number of credits and add that student as an instructor. Assign that student a salary of $30,000. Assume that there is no tie. There's only one student with that maximum credits, so no 2 students. So that way, we don't have a situation where 2 students have the same maximum credits. Well, same highest credits. This is just to simplify our query that we're going to write. Also assume that when you add this student as an instructor, they're not deleted from the table of students, because we actually need that for the next part. Problem 2, part D. Assign the student from the previous query to teach CS-001. So you are to write 8 different queries for these 2 problems. Again, they are adapted from problems in the textbook. In fact, they are based off of problems 3.11 and 3.12. They're just written a little bit differently from the textbook because, well, they're written a little bit differently because I wrote in basically different goals. So problem 1, part A and B, they build off of each other because, well, one is the logical opposite of the other. C and D, they build off of one another. Part A and B in problem 2 also build off of one another. Well, each step builds off of the previous one in part 2. But yeah, this is your filler assignment, homework 2. I'm going to give you about a week and a half to do this. So when you log into Canvas and you see this, you should, well, start on this as soon as possible, and then we can talk about it later next week as well. I'm also adding the schemas that you need to answer this as well. So for reference, this is the ER diagram for the university enterprise that the textbook is using as an example, and these are all the relevant schemas needed to answer all the questions. Let me just fix this up. There we go. So yeah, this is the ER diagram for our university example, and this is the schemas necessary for solving all the problems. All right. So that is your homework instructions. Let's talk about Chapter 4 now. Well, actually, before that, we need to finish up Chapter 3, because part of this assignment requires knowledge about Chapter 3 that we have yet to get to. So, I split Chapter 3 into 3 parts. Well, I split up Chapter 3 into 3 PowerPoint presentations. So this is Part 3. Everything that we talked about so far was set operations. Well, this is from Part 2. Part 2 was set operations, aggregate functions, and nested queries. The last part to talk about in Chapter 3 is how to update a database, how to add new data, how to update new data, and how to delete data. So let's look at that. So deletions work like queries. Tuple sets satisfy the where clause are deleted. Values for individual attributes cannot be deleted. Delete only applies to one relation at a time. If you want to update multiple relations, you need separate queries for those. If you omit the where clause in a delete statement like this, you delete everything from a relation. That just empties out the relation. All you have left is an empty table. So this is deletion. Let's look at a few examples. So, delete from instructor where department name equals finance. So basically, we're just gonna fire everyone from the finance department. Here's another one. Delete from instructor where salary between 13,000 and 15,000. So we're gonna lay off all the lowest paid instructors. Oh yeah, delete statements like this can contain subqueries. So, delete from instructor where department name is in this subquery. So we're just gonna remove everyone who works in the Watson building. Let's look at one of these in greater detail. So, delete from instructor where salary is less than select average salary from instructor. So we're gonna try our hand at removing instructors from our university whose salary is less than the average. So this requires evaluating the subquery, select average salary from instructor. I'm not going to go through that right now, but here is the result. I believe we went through it in the previous slides, so I'm just going to pull it out from there. So this is the average salary of all instructors. Then we compare each instructor's salary against that. So if a tuple's salary is less than the average, it's deleted. Right now, the slides is the wrong tuples have been crossed out. So really, it should be the ones that are not crossed out that should be the ones that are crossed out. But the result is this. So this is the table of instructors, but we removed everyone whose salary is less than 74,833. With an operation such as this, the average must be calculated before you do any tests. Otherwise, the average is going to change every time we do any sort of deletions, and the result will depend on the order. Yeah, so when we do deletions like this, you gotta calculate the average before you do any tests. Otherwise, the order of operations might change the average. Now let's talk about insertion. You can insert a new tuple to insert, or Okay, so you can provide either a new tuple to insert or a query that returns a set of tuples to be inserted. So insert into relation values or insert into relation a select from where statement. To insert a new tuple, specify the relation and the values for each attribute. Values must be in the order specified in the relation schema. However, users might not be familiar with the order of attributes, so if you know the order of attributes, you can just list the values in order of those attributes. If you are not familiar, you can just list out the attributes and then list out the values according to the order of attributes. You can even change the order of the attributes as long as the values match up with those attributes. So, we want to insert a class whose title is Database Systems and whose course ID is CS437. Just make sure those match up because the title should be Database Systems, not CS437. The course ID should be CS437, not Database Systems. Tuples that are the result of a query, you can use that as stuff to be inserted into another table. So let's consider this query. Music students with more than 144 credits, let's add them as new instructors with a salary of $18,000. So insert into instructor, select ID, name, department name, 18,000 from student where department name equals music and total credit is greater than 144. It's important to evaluate the select statement fully before insertions are performed. If insertions are performed while the select statement is still being evaluated, you will end up with an infinite number of tuples being inserted. With this example, the first tuple of student is added, the select star statement then finds it again and inserts another copy of the first tuple, and so on to infinity, ad infinitum. This does not happen with a primary key constraint, however. Null values may be assigned as values for attributes if there is no constraint that disallows null values. If a query were performed on student 3003, if a query were performed on student 3003, such as with this query, it can't be determined whether their total credits is greater than 45. So, we add in a student whose ID is 3003, and we don't know their credits. It also means that this query will not pull up this student here. Also, we might want to update values in a table. We previously had a discussion on doing arithmetic operations on tables, where we applied a 10% raise on instructors, but that only affected the values in the output table of our query. What if we wanted to commit those values? Then we'd use the update statement. So this was the query that showed a 10% raise applied to all instructors. If we want to commit those changes, the query for that should be update instructor set salary equals salary times 1.1. Updates may be made to tuples that satisfy the predicate specified in the where clause, such as granting a raise to selected computer science instructors. So, this query is the same as the previous query, update instructor set salary equals salary times 1.1, but with this where predicate, with this where statement here, the where clause, we're only applying it to computer science instructors. Here's another one where the where clause says apply that raise to instructors whose average salary, no, apply the raise to instructors whose salary is less than the average. When performing updates like this, it's important to do them in order. For example, consider these two updates. Update instructor set salary equals salary times 1.03. where salary is greater than 100,000. Followed by another update. Same update, same same thing to the instructor table, except we're applying a 5% raise to instructors whose salary is less than or equal to 100,000. So you can write it as two updates, but the thing is, this is the correct order. If we reverse the order, that might result in the wrong thing. What I mean is this. If we applied the second query first, this raises instructors' salaries so that they are this raises instructors' salaries for those who have salaries less than 100,000. That might raise someone's salary to be above 100,000. So when we apply the next query, we just gave someone a double raise. We don't want that. So this is the wrong order. This is the right order. If we want to prevent mix up like that, we could instead use a case construct. Update instructors set salary equals case. When salary is less than or equal to 100,000, then salary times 1.05. Else salary times 1.03. And here's the general form for the case construct as well. So case, one predicate, then result. One predicate, then result. Else default result, end. And that's the end of our discussion on chapter 3. Chapter 4 is intermediate SQL. Let's talk about that now. So this here is chapter 4, intermediate SQL. We're going to cover more about SQL. We're going to cover more complex queries. We're also going to look at view definitions and transactions. But before we begin, let's introduce a few new relations that we're going to be using for our upcoming examples. The first one is the student relation. It's a table of students, their departments, and their total number of credits. The next one is the takes relation. Basically, it's a record of all the classes each student has ever taken and what grade they had received. Grades are null if the student has yet to be awarded a grade. Remember natural join? That is a join operation that combines tuples from two relations if those tuples have matching values for the same attribute. And adding the using attributes clause allows us to specify which attributes to equate. So the first thing to talk about is the on condition, which works like the where clause, where a predicate can be specified. So select attributes from relation, join relation on predicate. So let's try an example. So select star from student natural join takes. So this is a review of how natural join works. Basically, we take each row in our tables and combine them with matching rows from the other tables. So let's look at this first row here for student Zheng. So the matching attributes between the two tables are ID and ID. We combine this. So we concatenate this with this row here. And then we concatenate this row with this next row here. So the result of that operation is this table here. Let's do that same operation again, but add on student ID equals takes.id. So the result of this is nearly identical, except there are two ID attributes, student.id and takes.id. In fact, this relation can be produced by performing a different query. It's this one. Select star from student, takes, where student.id equals takes.id. A query with an on condition can be written as an equivalent query using the where clause with the same predicate. So these two queries are the same. So we have yet another case where we have redundancy in SQL. But again, this is a good thing because one form might be more readable than the other. The fact that there is more than one way to arrive at a solution in SQL means that people who think about arriving to a particular solution can think about it in a way that feels most natural to them. So first, the on condition is associated with the outer join operation, and it behaves differently compared to the where condition. We're gonna have to explain what an outer join is, and that's literally in the next section. And again, the fact that SQL has more than one way to do something, more than one way to do the same thing, means people can think about arriving at a solution in a way that's most natural to them. Okay, we have to talk about natural join now. No, outer join. So let's bring back this query. Display all students by an ID and name, their associated departments, their total credits, and all information regarding the courses they have ever taken. So select star from student natural join takes. And the result of that query is this relation here. However, there's a problem. We forgot a student. So, look at the student and takes relations. We have a student named Snow who has yet to take anything. So their total credits is 0. And because their total credits is 0, because they've never taken anything, that means there is no information in the takes relation regarding Snow. Snow has never taken any courses, their total credits is 0, but it also means that the takes relation has no information on Snow. If we perform this natural join operation on these two relations, we're going to leave out Snow. If we do outer join operations like this, and in general, if we do join operations, we might accidentally leave out information that we would otherwise want to keep. In this case, we want to include Snow in our output. And this is what an outer join enables us to do. There are 3 general types of outer join. Left outer join retains all tuples in the left relation. Right outer join retains all tuples in the right relation. And full outer join is just left and right combined. The steps of an outer join are as follows. Perform a join operation as you normally would. During this process, if a tuple exists in one relation without a matching tuple in the other, that tuple is added to the final relation with null values inserted for the missing values. We called this kind of join operation an outer join. All the other join operations we have talked about thus far, we call those inner joins. In the case of Snow's information going missing, what we want is a left outer join operation because it was the left table that had Snow's name on it and the right table that did not. So to conserve Snow's information, to make sure that our output has Snow on it, we want a left outer join because it was the left table that had Snow's name on it. More specifically, since we're doing a natural join operation, we want a natural left outer join. So the full query for this is as follows. So let's walk through the steps of that. Okay, so we're going to perform these steps of a natural join as we normally would. So we take the tuple for Zhang and the corresponding tuples that have the same ID. We concatenate them to produce these 2 rows in our output table. We do this again for Shankar, and then we keep going until we reach Sanchez. So now we have these 2 rows combined together, and then we've added it to our output table. Who's next? Snow's next. So now Since snow doesn't have a corresponding tuple in the takes relation, what we're going to do is pretend we added in a row full of nulls, and then we just concatenated that with snow's information. So the row that we add contains snow's information, except it has null values for all the information that's missing, that's otherwise missing in the takes relation. So nowhere in the table does this row of null values actually exist. I just added that in for illustration purposes. We say that snow's data is padded with null values. And the result of that is this table that now contains snow and null values for everything that's otherwise missing. By the way, we can also add the on condition to an outer join. This query uses left outer join instead of natural left outer join. The only difference is the fact that there are two ID columns. Let's further discuss the difference between on and where. The difference is the on condition is part of the join specification, but if the predicate is in the where clause, then that condition is not part of the join specification. With the on condition as part of the join specification, from student left outer join takes on student ID equals takes ID, because there's no tuple in the takes relation containing snow's ID, that missing information is padded with null. That means we add snow's info to our output relation. If the predicate is moved to the where clause in our Cartesian join, with the predicate moved to the where clause, we perform our Cartesian join, and due to the join condition on true, no null padded tuples are produced. The end result that is we leave out snow's information. So we have outer join and inner join, but we also have left outer join, right outer join, and full outer join, and we also have outer natural join and outer regular join. Those can also use the on predicate clause and the using clause. The keyword inner can be added to any join operation, but since the default is an inner join operation, adding the keyword inner to a join operation doesn't do anything to it. So we can have inner, left, right, and full outer join types with these different join conditions. So natural join with an on predicate or using. So yeah, so that is outer join versus inner join. Let's talk about views now. Up until now, we have been operating on the logical model level. We've assumed that the relations we've been given are the actual relations stored in the database. In other words, we have full access to all the information in the database. This includes information that should be kept confidential due to security or privacy. But on the other hand, this might be too much information for us. People who access data in a database only ever access a small portion of data at a time. So, we're working with too much data, and some data may be confidential. So, to that end, we could produce other relations that contain only the information we need or are allowed to view. For example, a listing of all Fall 2009 physics classes. We can just then save that as a table and make it available to users. However, there is a problem. If we make changes to the original tables, course and section, we have to update them so that the table for Fall 2009 physics courses Every time we change course and section, we have to update the fall 2009 physics classes table. So storing the results of a query like this is generally not a good idea because we have to update it every single time. So instead, we define what is known as a view, a virtual relation, or as I've seen once, a query that pretends to be a table. So we can turn this query and define it and use it as the definition for a view. So this is the command for creating a view. Create view name as query. So here's an example. Payroll employees are authorized to look at instructor salaries, but no one else. So we can create a view that hides instructor salaries from others. Let's call that view faculty. And we define it as a query that selects everything. Okay. So payroll employees want to work with the instructor relation because that's the relation that has salary information. For everyone else, they don't get to view this. Instead, they get to view a abridged version of the instructor relation that we're going to call faculty. We define that relation as a query that selects everything but salary. So here's the faculty view. Now, nowhere in this database is this table actually stored. Rather, whenever we use this faculty view in a query is when we perform this query down here, select ID, name, department name from instructor. So, this is what I mean by views are queries that pretend to be tables. Here's another example. So this is the query that produces a listing of fall 2009 physics classes. We can use that to define a view. Let's call it physics fall 2009. So this is the query, and here is the same query used to define a view for physics fall 2009 courses. Once we define a view, we can use it as though it were a relation. For example, we can write a query that shows all 2009 physics courses that take place in the Watson building. Not by querying the course and section relations, but by querying the virtual relation physics fall 2009. So, what we can do is, once we define a view, we can use it as part of a query. Attribute names of a view can also be explicitly stated as shown here. In this case, there are two attributes. However, the expression some salary does not have an attribute name, so we need to name it here. Oh, by the way, we can use views to define other views. So, we previously had a view for Physics Fall 2009 courses, but we can define another view that uses that view as part of its definition. So, let's call this one Physics Fall 2009 Watson. So this is a view defined in terms of another view that is a virtual table of all Physics Fall 2009 courses that take place in the Watson building. Since Physics Fall 2009 is defined by a query expression, this view definition can be equivalently expressed by substituting Physics Fall 2009 with its query expression. So, the point of expressing views in terms of other views is, well, this is just easier to read. Since we have one view already defined, we can use it as a definition for yet another view. So, really, this is a simplified version of this. These two are the same, but one's easier to read than the other. Remember, when a view is defined, the query expression associated with it is not computed and stored. Rather, its computed on the fly. It's computed on demand. Even if the database is updated, it's only re-evaluated once the associated view is used in a query. However, sometimes there are cases where we want to save that table. These are called materialized views. Some database systems allow relations to be stored. So, views are defined as a query that is processed on demand. But sometimes it's useful to process it and then save it. These are called materialized views, and the process for maintaining these is called view maintenance. Although we won't get into deep about this, the basics are as follows. Sometimes it's useful to save a view. This can speed up computation since the view is pre-computed. However, you need to weigh the benefits of this against the cost of storing it and how frequently or infrequently it should be updated. If it's updated too infrequently, the materialized view might risk becoming outdated too soon. SQL doesn't provide standards for materialized views, but there are extensions made for this purpose. Okay, so once we have defined a view, we can use it as though it were a query. We can do queries on a view. What happens if we try to do updates on a view? So for example, we have this faculty view. Remember, everyone else gets the faculty view. Only payroll employees would get access to the full instructor relation. So what happens if we take that faculty view and try to insert a new instructor into it? So the faculty view is defined by a query that uses the instructor relation, which has the salary attribute. However, the faculty view does not have an instructor attribute. So, there are two reasonable approaches for evaluating this query here. Insert into faculty, instructor Green into the music department, whose ID is 30765. Approach number 1. We add it anyway, but the salary is null. Approach number 2. Don't add it, present an error message if you tried. And both are pretty reasonable ways to go about processing this query. But here's a more problematic example. So, instructor info is a view defined using two tables. If you look at those two relations, which is part of the definition of instructor info, we find we have no tuple with the ID 69987. We don't have a tuple with the name White. And although there is a Taylor building, we don't know what White's department is. If we went forward with inserting information into instructor info, and since instructor info is defined using as a query that uses these two tables, we have to insert something into both tables. So the most reasonable thing to insert into the instructor relation would be 69987 White null null. And the most reasonable thing to insert into the department relation is null Taylor null. Again, this is all because we have no idea what department White is in. And because of all these complications, we're not allowed to do this at all. So, modifications on view relations are generally not permitted, except for one special case. A SQL view is updatable if the following conditions are satisfied. The from clause has only one relation. The select clause contains only attribute names from the relation and does not contain expressions, aggregates, or the distinct keyword. Any attributes not selected in the select clause allow null values. And There is no group by or having clause. Different databases might have different rules about this. So, create view name as select attributes from relation where predicate. So a view such as this, create view history instructors as select star from instructor where department equals history. This is an updatable view because it satisfies the 4 conditions listed up here. The from clause only has one relation. Check. The select clause only contains attribute names from the relation and does not contain expressions, aggregates, or the distinct keyword. The select clause contains only attributes from the relation. Check. There is no expressions or aggregates or distinct keyword. Check. Any attributes not selected in the select clause allows null values. Well, we're selecting everything, so that does not necessarily apply here. Check. And there is no group by or having clause. Also check. However, even with these conditions, issues can still arise. And it is this. We have this view of history instructors, but how it's defined doesn't stop us from adding biology instructors through it. So this will work, but it feels off to add biology instructors through the history department. That's a little weird. What we can do to prevent that is to add with check option to our definition for history instructors. So create view history instructors as this query with check option. So now, if we want to add Brown as a new biology instructor, it must go through the biology department. I'm assuming that there is a equivalent view for biology instructors. So create view biology instructors as select star from instructor where department name equals biology with check option. So we can only add Brown, not using insert into history instructors, but rather insert into biology instructors. So that's the proper way to add Brown as a biology instructor. There are even more rules regarding updating a view, but they're way too complex to discuss here. Let's talk about transactions. A transaction is a sequence of query and or update statements. A transaction implicitly begins when a SQL statement is executed and ends explicitly when one of 2 statements is encountered. Commit work, everything's all done, let's commit all the changes, and we're good. Or rollback work, where something went wrong with your sequence of queries and you just want to reset everything to how it was before you started. In essence, all SQL statements, queries, and updates within a transaction are performed as one big atomic or indivisible operation. All or nothing. Since changes are committed once commit work is encountered, in the event of a power outage because commit work cannot be entered, the database is reverted to how it was before all work began. Similarly, if a sequence of SQL statements could not be completed successfully, rollback work reverts everything to how it was before you started. By default, however, each SQL statement is its own transaction. This is something that we have to turn off to treat a sequence of statements as one transaction, but this requires us to turn it off, and the means to do that depends on the implementation. So a better alternative is to begin a transaction with begin atomic and then end it with end. So between begin atomic and end is all your statements that you want to execute as one big atomic operation. Hey, remember integrity constraints? So these are rules that ensure data remains accurate and consistent within a database. They also guard against accidental damage. In practice, an integrity constraint can be some arbitrary predicate, but the more complex the constraint, the more costly it becomes to test. We've seen a few examples of integrity constraints, and these ones are simple enough to test with a very minimal overhead. For example, an instructor's name cannot be null. No two instructors cannot have the same ID. Every department in the course relation must have a matching department in the department relation. That's a little bit more complex, but still pretty easy to test. And a department budget cannot be 0 or less. Must be greater than 0. There is another set of integrity constraints called functional dependencies that is discussed in Chapter 8. But when we define a table using the create table command, we can add integrity constraints to it. We can also add integrity constraints to a table after it's been created using the alter table command. So create table relation attribute data type and then integrity constraints, or alter table relation add constraint. So when we define a table using create table, we can add 3 different integrity constraints: not null, unique, and check predicate. Not null is pretty simple. Basically, it disallows null values for that attribute. If you tried to enter a null value for that attribute, you get an error message. In SQL, null values are disallowed if an attribute is part of a relation's primary key, but there are other cases where you want to disallow null values, not just the ones for primary key. The unique integrity constraint specifies that for a set of attributes, no 2 tuples in the relation can have the same value for all those attributes. So here's an example. So unique ID means all. Okay, so if we added unique ID to the instructor table, it means every instructor must have a unique ID. However, if we had our primary key to be all 4 attributes somehow, that is ID, name, department, and salary. If somehow our primary key was all 4 attributes, really it shouldn't, but even if that were the case, you could have 2 instructors with the same name, working in the same department, and with the same salary. You can have all of those be the same, but one attribute, at least one attribute, must be different between the 2. And in our case, this would be the ID. The check clause, check predicate, can be added to ensure every tuple in a relation satisfies the predicate. A simple check would be something like this: check that the budget is greater than 0. Here's a more complex example. This specifies that the semester attribute of a class section is in the set of seasons fall, winter, spring, summer. This makes the check clause more powerful than most type systems in most programming languages. Hey, remember in referential integrity? I've talked about this quite a lot, and basically, if you have something in a table that references something else, that something else must also exist. The more formal definition is as follows. The values that appear in one relation for a given set of attributes must appear for a certain set of attributes in another relation. We've seen one example with the foreign key clause back in Chapter 3. That can be added to a create table statement. Foreign key attribute references reference relation. So in practice, it would be part of the create table command, where foreign key department name references department. This basically means that we can't add courses unless the relevant department exists. We can't add instructors unless that relevant department exists. And we can't add sections for a course unless that relevant course exists. Without those constraints, we can add courses for non-existent departments, or instructors for non-existent departments, or sections for non-existent courses. That's something we want to prevent. Therefore, primary and foreign key constraints. Before we continue, let's also update these commands so that they contain the new constraints we've added so far. So basically, let's update them so we have our check constraints. They're all pretty simple to understand. Check that the semester is fall, winter, spring, or summer. Check that the year for a section is between the year 1759 and the year 2100. check that the table course has credit counts that are greater than 0. So a course should be valued at greater than 0 credits. An instructor, their salary must not be below the salary of an instructor must be greater than this minimum of 29,000. Here's 2 more for classroom and department. It's only the department that has a check clause, and that is make sure the budget is greater than 0. By default, a foreign key references the attributes of the reference table's primary key, though there is a shorthand for that as well. Here it is. Department name varchar 20 references department. So this department name attribute is referencing the same attribute of the same name in the department relation. Hey, what happens if a update violates a referential integrity constraint? So, the normal course of action is to just reject that action. Whatever transaction caused the violation is rolled back. Deletions and updates, however, get a lot more complex, and in short, the course of action depends on how these tables are set up to handle updates regarding referential integrity. So if, for example, we have a class that takes place in a classroom, a class section that takes place in a classroom, but we delete the classroom, what happens next? Well, depending on the course of action, we can either reset that classroom to a default classroom, or we can delete the class altogether, or we just don't allow that update to happen. If a class section takes place in a classroom and we delete the classroom, either the classroom is reset to a default classroom, or the class section is also deleted, or we just don't allow that update to happen. I'm gonna leave this part of our discussion for next week. So that's gonna be it for this week's discussion on Chapter 4. We have quite a bit more to talk about next week as well. That includes our discussion on what happens with referential integrity if you try to delete something that's being referenced. So, I'm going to leave it here, and we're going to continue our discussion next week. All right? Take care, and if you have any questions about the homework, definitely feel free to email me, and yeah, that's it. That's it for this week. Next week, I'm going to have your next live as well, and yeah. All right, bye.